Perspective Class 13 Video 2. In this video we're going to talk about image size, in particular image size with regard to central projection. So let's look at a picture to see what's going on. So in this picture we see the object is this blue line segment right here, okay? And it has a particular size, it has a particular length, and we centrally project it onto our viewing plane, which is the x equals d plane, and it becomes a smaller size. And the question is, how do these sizes relate to one another? So how does the actual size of the object relate to the image size of the object after central projection? Well, not surprisingly, the image size depends on many different factors. So the image size depends on three factors. Okay, the first one is the actual size of the object. Okay, like if the object is bigger, then the image size is simply going to be bigger as well. The second one is the distance of the object from the viewer. So in this case, that is the distance big D, because that is how far away the object is from the eye, from the viewer. And the final one is the distance of the image plane. From the viewer. And that is lowercase d, the distance of the image plane. And you know, this sort of makes sense, because if you can imagine moving the image plane closer or further away from the eye, like if you imagine moving the red line here, well then the blue bit is going to be smaller. Okay, so all of these factors, all three of these factors, determine how large the image is. And in fact, the relationship between these three factors and the image is pretty straightforward. It's given in this theorem right here. So this theorem says if we centrally project an object on the x equals d plane onto an x equals lowercase d plane, then the image size is related to the actual size like this. The image size is d divided by capital D times actual size. And the same formula is true if we replace x with y or z. Right? There's nothing special about projecting onto the x plane. You can also project onto a y plane or a z plane, and the same formula is true. So this formula, if you know anything about similar triangles, it's just a basic statement in similar triangles. That's all I'm saying. You could sum this formula up as saying like, this small triangle is similar to this big triangle, therefore the ratio of the side lengths are equal. But we don't need to worry about that. All that matters is that you can actually use this theorem to work out some examples. So let's try and do an example right now. Okay, using this theorem, let's try and do an example. So here's a setup. A tree is 120 feet tall, and it's 225 feet away from the viewer. If we centrally project this tree onto a plane which is 1.5 feet from the viewer, how tall will the image be? So like if you're painting this tree, it's a 120-foot tree, you're standing 225 feet away from it, and your canvas is 1.5 feet in front of your eye. How big should you draw the tree? Okay, well, we just use this theorem right up here. So the image size is going to be equal to, so lowercase d is the distance of the viewing plane, which is 1.5, divided by uppercase d, which is the distance to the object, which is 225. This is all given in the question, times the actual size, and the actual size of the tree is given as 120. And if you use your calculator to work this out, you'll get 0.8. So you should draw the tree 0.8 feet tall on your canvas. And that's the end of this question. Okay, that's the end of this video.